said you would like us to.
And good Tuesday evening to you. Hi, my name's Gary, ham radio call sign Whiskey 4 Echo Echo Yankee. And this is an intermediate ham radio class. This is a class for people who have their existing technician licenses and want to move up to the next level, which is the general class. And we're about midway through the class. And you can actually find a playlist that this video is in on YouTube. Go back and catch up with us if you'd like. We're coming up on Chapter 5, and when I talk about chapters, I always like to show the book. This is the ARRL General Class License Manual, 10th edition. This is the most recent version of the license manual. It has the current question pool. The older books, the 9th edition, etc., have good knowledge in them, but the questions that they ask you to answer are different. Some markedly different, some not so much, but this is the book you want, the 10th edition. And tonight, as I mentioned, we're going to do Chapter 5, Radio Signals and Equipment. Before we get started, are there any questions from anyone in the group? Well, yes, you should be seeing me in the Zoom classroom. Can everybody else see me in the Zoom classroom? Yes, okay, I'm getting heads nodded. So again, Will, apparently you've got a problem. You might want to reboot and start again, come back in again. Okay. Any questions from anyone before we get started tonight? All right, let's go ahead and get started. We've got a lot of stuff to do tonight. We'll do the first 3 sections. We'll take our 5-minute break, and then we'll come back and finish the last 2. So we're going to start out with basic modes and bandwidth, and some of this should be some review from the technician class. So modulation, remember, is adding information to a radio carrier. So here's our radio frequency carrier signal. Here's audio, for example, in the form of a sine wave. And by varying the amplitude of this carrier, you then are having modulation imposed on the carrier, and you're able to transmit a signal that can be demodulated at the far end. So this is amplitude modulation. This is amplitude versus time. And the peak values of the carrier and the modulating signal make up this, which is called the modulation envelope. And we'll talk more about that in a second. And so this is in the time domain. This is what you would see if you hooked an oscilloscope up to the output, the attenuated output of an AM transmitter, for example. Now, if you hooked a spectrum analyzer up to the output of an AM transmitter, you'd be in the frequency domain. Spectrum analyzers work in the frequency domain, so they have amplitude on the vertical scale, and then frequency is on the horizontal scale. And you might remember that an AM signal consists of 3 components: the radio frequency carrier, an upper sideband, which has the modulation information, and a lower sideband, which has the same modulation information, just reversed. Low frequencies are closest to the carrier. So low frequencies are here for the upper sideband, low frequencies are here for the lower sideband, lower modulation frequencies of the voice. So what is the most popular ham radio voice mode on HF? Is it AM? It is not. It's single sideband. Single sideband transmits just either the upper sideband or the lower sideband, depending on where you are. We'll talk more about that here in a second. So that's amplitude modulation. Frequency modulation is a bit different in that the carrier wave, here's our modulation up here. The carrier wave is here, and instead of varying the amplitude, we vary the frequency. So when the modulation dips down, for example, it's a lower frequency. These are farther apart. And when it comes up, it's a higher frequency. They're closer together. So frequency modulation changes the instantaneous frequency of a radio frequency carrier. Again, the whole purpose of modulation is to convey information. And here's a close-up look of the modulation signal up here and what the envelope would look like with an amplitude modulated signal and what it looks like with a frequency modulated signal. All right, let's move on to a new one, phase modulation. It's a kissing cousin to frequency modulation, and it has, again, the modulating signal here, the carrier signal, and you can see that they're closer together here, but they're actually farther apart, but kind of odd-shaped here. Phase modulation changes the phase angle of a radio frequency carrier in order to convey information. And so very much like the FM, it varies the instantaneous frequency and also the phase of the modulated signal. So we're going to talk some more about this, phase modulation, frequency modulation, as we move on. So I wanted to talk about hams, and I purport that hams are opportunistic. That means that we take advantage of things, not unethically, but we look for strategies of how to make a successful radio contact. Well, what do I mean by this? Well, we take advantage of the conditions that exist at the time. Are there sunspots? Oh, is it daytime and sunspots? Well, probably you can make contacts then on the 10 meter and the 12 meter bands. That might work out. Okay, is the 20 meter band open? If it's not, well, maybe I can go to a lower frequency. Is there a DX contest running this weekend? I might be able to make some new contacts. So we look for conditions as they are. We go online and look up space weather and try to ascertain, okay, what's going to be good, and take advantage of it. So that's because we're amateur radio operators and we have that flexibility. Well, in the commercial world, telecommunications folks, they aren't that way. They seek reliable communications. That's the big thing. And so when they're communicating, they're setting up systems generally point to point and to communicate information reliably. And so a radio link, something that they would set up, is a radio circuit between 2 points. Well, as we move on in our ham career, we're finding that there's new things available to us. One of those is a ham radio mesh network. It's when you actually can modify commercial Wi-Fi equipment and use it to make data links between you and your other ham friends. It's independent of the internet, independent of the commercial services that you might get from your internet service provider, but ham radio mesh networks can be fun and can be highly useful in emergency situations when you're trying to get information from point B to point A or point C or whatever. And these are usually set up well in advance and tested out, and they're engineered in advance. And some of the things you have to take into consideration for these radio links are, the distance, how far away is it, and therefore how much is the free space loss, because the radio signal dissipates as you go further out, and so we have to calculate that. We have to know about diffraction. Is there any sharp edges in the way that are going to maybe influence the signal? Multipath is always a problem. Are there going to be reflections? It could be additive or reflective. Is there foliage? Is there going to be absorption of our signal? Remember, we're talking about Wi-Fi here. We're talking about 2.4 gigahertz. Terrain. These are line of sight signals. So if you've got a hill in the way, that's going to be potentially a problem. And atmosphere. So for one of these ham radio mesh networks, these are all of the things that we have to take into consideration. So here's my proposed link. I want to put together a 2.4 gigahertz, 13 centimeter in the amateur bands, 2.4 gigahertz, 10 miles, and we'll start with 0 transmitter and receiver gains. And down below here, if you'll get when you get the handout, is a URL link to an online calculator for path loss. So you can put in the frequency and you can put in the distance, and it spit this out for me. The loss over 10 miles is going to be 124.2 dB. Also, you can find all sorts of stuff on the internet. The minimum Wi-Fi level that is considered appropriate in the commercial world is minus 80 dBm, or 80 dB below 1 milliwatt. When you see the dBm, that M refers to milliwatt. So knowing those things, we can start doing some calculations about our system gain. So remember, the path loss is 124.2. Minus 80 dBm means that we've got to come up with, if we start out with a milliwatt, we've got to come up with 44.2 dBm of gain in our system. And then we should also add fade or link margins, because one of those things like absorption or reflections or one of those other factors may come into play. So 10 dB is not a bad number for headroom. So we know that our system gain must be 54.2 decibels. And so gain then is the transmitter power above a milliwatt. That's one way. There's transmit antenna gain. There's receive antenna gain. And there's transmission line losses, which would be a negative to us. What we are building here is a link budget. We're engineering in advance for this radio link. And if you remember your decibels, if we say that 1 milliwatt is the reference, well, 1 watt is 1,000 milliwatts, so that's 30 dBm, that's that level. And 10 watts, which is the maximum we can transmit on the amateur radio 13 centimeter band with spread spectrum, is 40 dBm. So if we have 40 dBm, if we can transmit at 10 watts, and our desired system gain is 54.2, then we need to make up 14.2 dB in antenna gains. Now, I'm not trying to scare you. You don't have to do any of this. I'm just trying to give you background on links and a link budget. In the commercial world, this is something that they do all the time. They make sure that their towers are tall enough so it avoids terrain. They have losses coming up the tower, but then they have gains from the antenna. They have a certain amount of power coming out. You've got a path loss. And then you've got to receive, could be a cell phone with an antenna that may or may not have any gain. All of this builds the link budget, the signal budget for that circuit. So that's the definition. A link budget accounts for all power gains and losses in a system. And remember that 10 dB that I added in there? Well, that could be called the link margin. I call it headroom, and it's the difference between a system's the design level and the minimum power needed to receive a signal. So it gives you a little bit of room to maneuver should there be other factors that come into play. This is especially important with digital signals where it's an all or nothing situation most of the time with digital signals. It'll either be received perfectly or not hardly at all. All right, that's link budget and link margin. All that for 2 questions. Oh, questions. let's go ahead and see what we can do here. So go ahead and unmute, and let's try. What is the name of the process that changes the phase angle of an RF signal to convey information? Bravo, phase modulation. That is correct. And what is the name of the process that changes the instantaneous frequency of an RF wave to convey information?
Delta.
Frequency transformation.
It is delta frequency modulation. Remember, modulation is the process of adding information. And what type of modulation varies the instantaneous power level?
Delta.
That's amplitude modulation, where you're changing the amplitude of the carrier. And which of the following phone emissions uses the narrowest bandwidth? Remember, it's not AM.
Alpha.
I heard alpha. Yes, indeed. Single sideband.
Sideband.
And what is a link budget?
Charlie?
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 And everybody says Charlie, and you are correct. It is the sum of the transmit power and antenna gains minus the system losses as seen at the receiver. And what is link margin?
Bravo.
It is Bravo. It's the difference between received power level and the minimum that is required at the input to the receiver. So for these last two questions, we've had students say in the past, if you don't know, pick the longest answer. It proved correct here. All right, I'm going to push the mute all button, but if you get a request to unmute, just ignore that. All right, we are all muted. And let's move on to section 5.2. We're moving right along, and that's good because we've got a lot of stuff to cover. You want to be a competent amateur radio operator. And a competent amateur is one who knows their radio, and it takes time to learn these radios. They're so darn complicated sometimes. And to know your signal, the signal that you are transmitting. So whether it's a sideband signal or a CW Morse code signal or an FT8 signal, you need to know the characteristics of that in order to be a competent amateur. So here's our old friend, the ICOM 7300. And if you notice here, it says 7073. So does anybody know what band that's in? Seven megahertz?
40?
Is the 40 meter band. Yay, you get the gold star. All right, and if we look very close to this, it says lower sideband. So, okay. Lower sideband signals. We've said that sideband signals are about 3 kilohertz wide. Okay, I'm going to keep that in mind. But, oh, this frequency, 7073, what is that indicating? And the answer is down below. Unless your manual states otherwise, and it's very rare to find a radio that's not this case, it indicates where the carrier frequency is if the modulation were to have a carrier. What? So remember, we're talking about a lower sideband signal here. So that's here. Remember, we said it's going to be about 3 kilohertz wide. And this is where the carrier would be. But remember, with a single sideband signal, the carrier goes away and the upper sideband goes away. But this is what the radio will indicate. That 7073 is this point right there. And then you need to know that with lower sideband, your radio frequency transmission extends 3 kilohertz below that frequency because it's lower sideband. If it were upper sideband, then it would be 3 kilohertz above the indicated frequency. So for single sideband, the frequency indicated on your radio is the carrier frequency if there was a carrier frequency. Here we are, 14235, that's in the 20 meter band. And we're in upper sideband, because remember the rule is 9 megahertz. Below 9 megahertz, we use by convention lower sideband, and above 9 megahertz, we use upper sideband. And we mentioned the occupied bandwidth is 3 kilohertz. Okay, so here we're back on the 40 meter band, 7150, and that must be the indicated frequency on our radio. And here's our 3 kilohertz lower sideband signal. Anybody have their color chart out handy? What class of license does this ham have, we hope? If you look at your color charts, this is in the advanced and extra class portion of the 40 meter band. So a general class operator actually could not operate on this frequency. And that's indicated. Well, if we go over to the calculator cam, for example, this is the 20 meter band, which is very similar. There's a cutoff here at 14,225. Up here is the single sideband portion. Remember, it's always in the upper part of the band. And here's where generals can operate, from 14,225 to 14,350. Here and here are where advanced class and extra class operators can operate. And that's where the rare DX usually is down there. So that's why you're going to want to upgrade when you get a chance. So continuing with the single sideband mode, we're here on 20 meters. Remember, we have an occupied bandwidth of 3 kilohertz because it's a upper sideband signal. And our radio is indicating 14,350. What's wrong with this picture? If you look at your color chart, go ahead.
It's in a different band.
It's out of band. Yes, our band ends at 14,350. And so if you transmit here, you're over the edge. You're over the edge of the band, and the RF that you are emitting is not in a ham band. Even though the radio says 14,350, remember your signal is actually 3 kilohertz above that. And so that's something that we always have to be mindful of, is where the edge of the band is, or where the edge of our license segment is. If we get our general class license, then we have to know where the bottom end is. All right, so that's for single sideband, 3 kilohertz wide signals. Well, if we're going to transmit AM, that's a 6 kilohertz wide signal with both an upper and lower sideband, and the radio frequency that's going to be on the radio is where the carrier is. So we have to be mindful that we have a wider signal here. Single sideband 3 kilohertz, AM 6 kilohertz. All right, this is a little aside. It's not necessarily a test question, but you might, especially those coming from the CB world, remember the marketing between AM and single sideband, and everybody said, oh, single sideband has more talk power. It's not that the signal itself has more talk power, but consider this. We'll use an amateur radio transceiver, 100-watt amplifier in a ham radio transceiver. If it's having to amplify an AM signal, which consists of a lower sideband, an upper sideband, and that carrier signal, well, that 100 watts is going to be divided among all 3 of those components, and so you're only you're going to get a strong signal coming out. But if you can use that 100-watt amplifier to just amplify the one sideband, all of this can be added to this, and so you look at the 2 size differences here. You're going to have more signal using single sideband transmission. So if you ever hear the phrase talk power, that's what they're talking about. So Morse code. Okay, I got my radio now set in the CW mode. Here I am on 7073. That might not say CW, but assuming that it does. With CW, the indicated frequency is the frequency that you will transmit on. And you think, okay, great, so I'm only going to transmit on one frequency. No, just the act of sending Morse code, whether it be by hand or with a keyboard or a paddle or whatever, that adds information to the radio carrier, and it also adds bandwidth. Not a lot. So here's an unmodulated radio frequency carrier. And here is a CW signal when you're actually sending, and the bandwidth is probably about 150 hertz, thereabouts. The bandwidth depends on your transmitter's keying rise and fall times. And these are adjustable in most transmitters. A very fast rise time and fall time means a wider bandwidth signal. Also, it's going to sound kind of clicky. So here's on a spectrum analyzer, occupied bandwidth of a Morse code signal, about 150 hertz. All right, let's go back to our old friend that we mentioned earlier, FM. Those Baofeng HTs, or your Yaesu or Kenwood or whatnot, they're FM HTs, likely, unless they're one of the new digital modes. FM is generated by modulating. Here's an audio signal, here's a microphone being amplified, and we come to a reactance modulator right here at the oscillator stage of the radio. This is an amplifying transistor, and if you remember that an oscillator has an amplifier and a feedback loop. Here's our tank circuit that sets the frequency, and so we modulate FM right at the first oscillator. So modulation applied directly to a radio's oscillator yields frequency modulation. Its kissing cousin we talked about earlier, phase modulation. Here we have the oscillator running on its own, and it comes into a follow-up stage. The audio modulation comes in and is applied across a varactor variable capacitance here. And this is after the main oscillator, so this reactance varies with the amount of modulation applied. Modulation applied to a point after the first oscillator yields phase modulation. And in FM, the frequency is changed by the modulating amplitude of the voice signal, for example. In phase modulation, it is changed by the modulating amplitude and also by the modulating frequency. So lower tones do not modulate as much phase modulation as higher tones do. Keep that in mind. FM modulation is done at a low-level oscillator stage, phase modulation done at a higher level amplifier stage, and both are called different types of angle modulation. Just giving you some background here. And here's a look. They look kind of the same. Frequency modulation here, phase modulation down here. And in fact, a radio receiver that can receive FM can also receive PM signals and vice versa. There are some special considerations that come into play. We won't go into them here. Oscillators, I talked about that earlier. It's an amplifier with a feedback circuit that filters on one frequency. And so an amplifier with positive feedback through a frequency determining filter, that's known as an oscillator. And one of the best oscillators, the most stable, are those that employ crystals in the filter section. A crystal oscillator has excellent frequency stability. It's very hard to pull it off frequency, but it's limited to that one frequency that the crystal is designed for. They actually sand the crystal surface down and make it a certain mechanical distance, and that sets the vibration and sets the frequency that the crystal will resonate at. And a crystal is really electrically very much like a tuned circuit with an inductance and a capacitance, with a certain internal resistance, paralleled by a shunt capacitance. That's the equivalent circuit of a crystal. More common in less expensive radios are LC oscillators. variable frequency oscillators in tube-type radios, for example, consisted of tank circuits with either in parallel a capacitor and an inductor, a resonant circuit, or it even could be a series resonant circuit. We're not going to go over the formula, but this is the formula for a resonant circuit. And all I want to point out here is that inductance in henries, capacitance in farads, it's 1 over. So the more inductance or the more capacitance you add in a tank circuit, the lower the resonant frequency is going to be. Oh, this is not a tank circuit. No, this is a tank circuit. This is a parallel resonant circuit with an inductor and a capacitor coupled back to the input of the amplifying transistor. And pictorially, this is another way you could draw the same thing. And it's the values of L and C in the tank circuit that will determine the oscillator frequency. And if you make one of these variable, a variable capacitor, for example, then you can change the frequency of that oscillator. So we've talked about crystal oscillators and we've talked about LC oscillators. Well, there's another type to know about, and that's the direct digital synthesizer. And its beauty is that you have variable frequency, like you do with an LC oscillator, but you have crystal oscillator stability. Because the LC oscillators were notorious that as they would heat up, as the tubes inside would heat up, they'd change in frequency. But DDS systems don't have that problem. And just for background, direct digital synthesizers are made up of a phase accumulator, a lookup table, a digital to analog converter, a low-pass filter, and it doesn't have any phase noise. Is something that's advantageous for direct digital synthesizers. Okay, we cover a lot of different disparate material in this chapter, so hang in there. Heterodyning. This is a process, a signal process invented in 1901 by a Canadian, Reginald Fessenden, and what it does is it creates new frequencies by combining or mixing two signals together. And this is the schematic diagram for a mixer circuit or pictorial diagram. And for example, here's our radio signal in the 40-meter band, 7.150, coming in here, and we mix it with a signal from one of our oscillators. Could be an LC oscillator, could be a DDS oscillator, could be a crystal oscillator, although not likely. And what happens is 7150, 7605, our desired output is 455 kilohertz. That's a common intermediate frequency output on super heterodyne radios. It's where a lot of the amplification occurs, is at that frequency, 455 kilohertz. And the oscillator provides on the output the two original frequencies, the sum of both of the frequencies, and the difference. So in this case, 7.605 minus 7.150 gives you 455 kilohertz. So this is mixer math. Two signals coming into the mixer, 4 signals come out. And then you use filters, IF transformers, for example, to filter out the unwanted signals. And in a pictorial, here's our mixer stage. Here's our local oscillator. Here's the RF signal coming in that we want to receive, the IF amplifiers, and then maybe an audio stage and a speaker. Superheterodyne was used in early VHF radios. This is probably from the 50s or 60s. This is a mobile radio. How'd you like to have that in your car? Or systems like this one. I think that was a GE. This is a Motorola. Where do you put this stuff? Well, of course, you put it in the trunk. It was high technology at the time, mobile transmitter and receiver combinations. And this is what I want to point out. In this older equipment, we talked about the fact that if you're going to generate FM signals, you have to do it at the oscillator, the main oscillator, to give you an FM signal. And so this is actually AM. I'm looking at this now. But they would use, in order to get up to the VHF and UHF frequencies, they would have a main carrier oscillator, and they would have frequency multiplier stages. And then going out to a power amplifier, and I apologize, this is an AM transmitter, modulated class C power amplifier goes out to the antenna. AM predated FM in most applications. So here's a frequency multiplier stage, a transistor one based, and what you do is, let's say you have a 1 megahertz signal coming in, and you want to multiply that up to 2 megahertz. Well, by sending it into this nonlinear amplifier, it's going to have some of the original signal, but it's also going to have a second harmonic, 2 megahertz, that's going to be present, and you have a tuned stage, tuned to allow the 2 megahertz signal to pass and everything else to be blocked. So you can make frequency doublers and frequency triplers. It's a good use of harmonics. We're just introducing this concept. Now we're going to talk more about it specifically with a test question here coming up. So just stand by. And I mentioned radio frequency filters. You filter out what you don't want. Filters pass a portion of the frequency range while blocking the rest of the frequencies. And filters can be for transmit and for receive. They can come in various different design configurations. We're not going to go in depth on these. Here are some transmit filters, for example, probably a couple hundred watts. These are the kind of things that you would use at field day, for example, to prevent interference from one nearby transmitter or another on a different band. Schematically, this is what it looks like. You have the ability to select the various filters. And the filter characteristics, how wide a bandwidth the filter has, we use the half power points or the 3 dB points on their chart. You actually plot signal levels. So we're below the design frequency. As we approach the design frequency, signals are started to be passed, and then as we go higher, then it stops. So this is the 3 dB bandwidth. That's known as the bandpass filter's bandwidth. And anytime you put a filter in a circuit, you don't get something for nothing. So you might have a 10 dBm, 10 dB above a milliwatt signal coming in. You have a filter, and you've only got an 8 dBm signal coming out. You lost 2 dB in your filter. That is the filter's insertion loss. So whenever you put a filter in, you're going to get less out of the other side. And so that was a bandpass filter. You can also have low-pass filters, for example, that pass everything below a certain frequency, but at the half power point is when things start to be whacked off and you don't get signal beyond that point. So this is a low-pass filter. Oh boy, there's a lot of stuff here. You're starting to feel rejected. A filter has a characteristic called ultimate rejection. It's a filter's maximum ability to reject signals outside its pass band. So for this guy here, we would say from the signal level here down to the rejected point, that's 30 dB. So this filter has an ultimate rejection figure of 30 dB. Moving on, something completely different. Anybody know what this is? I spent a lot of time looking at one of these. This is for the old NTSC, the analog television system. This is a vector scope that is looking at a color bar signal, and here's the phase reference line here, and here's red, here's magenta, here's blue, here's cyan, here's green, and here's yellow. So all of the colors represented by the color bars, and you want to make sure that they appeared within the box. Well, the reason I'm pointing this out is that this was an analog use of I, this is the I axis, and Q. See the Q here and the minus I there? These are I and Q signals. And I and Q signals are very special. They can be in the analog domain or they can be in the digital domain. And by that I mean, analog signals are the things you can measure, with an oscilloscope, whereas digital signals are ones and zeros that represent a particular signal. I and Q can exist in both of these areas. And I stands for in phase, and Q stands for quadrature. And I and Q signals are signals in the same frequency range, but shifted in phase by 90 degrees. So here's two single sine waves, and they're in the same frequency range, and they're shifted by 90 degrees. Cosine waves and sine waves. And so these would be an analog representation of I and Q signals. So again, Q and I, and we're able to get all of the colors of the color bars out of those two signals. Interesting things happen when you add I and Q signals together. So here's a graphic representation of it, but the point I want to make when this happens is that with the right I and Q signals, you can create any type of modulated RF signal. You can put a very complex I signal and a very complex Q signal together and add them, and you get the desired RF signal that you want. It's maybe more difficult to do it in the analog domain, but in the digital domain, this sort of thing, you've got two simple signals up here, and you get a much more complex signal down here. So again, with the right I and Q signals, you can create any type of modulated RF. Likewise, any RF signal can be demodulated, again, using I and Q signals, where you bring the signal in, you separate it out into the two components, and then you have further stages here that can work on demodulating these signals. In this case, we have an analog system that shifts I and Q and then goes into an analog to digital converter and does work on it. This is the kind of thing that is happening with digital signal processing in a lot of amateur radio transceivers. It's a super heterodyne radio on the front end, but on the back end that's converted into digital, and then a lot of processing goes on. So again, the difference between analog signals and digital signals. And again, here if you want to look into it more, analog signals up on the top, digital signals on the bottom, and here's another URL you can follow to get much more information that is necessary for you to pass the test. So where does all this happen? Well, it happens in the more modern, the newer amateur radio software-defined radios. This is my Flex 6600 that I have over in the other building, and it's a complete amateur radio transceiver, 100 watts, that has no knobs or dials, just connections on the back, and you use a computer to control it. And it can be computer software running on a laptop or on a Mac or PC, or it could be on an iPad, or it could be their Maestro controller. All of those allow you to do all of the control functions you would do on an analog radio with this digital radio. Software-defined radio is where all of that activity happens in the digital domain. All right, let's answer some questions. Which of the following are basic components of a sine wave oscillator?
Delta.
Delta.
You see that? Yeah, it's a filter and an amplifier operating in a feedback loop. And what determines the frequency of an LC oscillator?
Charlie.
Bravo.
It is Charlie. It's the inductance and the capacitance, the L and the C in the tank circuit. That's why they call it an LC oscillator. And which of the following is characteristic of a direct digital synthesizer?
Delta.
Yeah, we didn't go in depth with it, but it has a variable output frequency with the stability of crystal oscillators, and a lot of amateur radio transceivers utilize this technology. So what term specifies a filter's attenuation inside its passband?
Bravo.
Delta.
No, you can't get something for nothing.
Bravo.
Alpha.
It is alpha. When you put a filter in, when you insert a filter, it's going to attenuate the signal slightly. We showed the example of 2 dB, which would be about typical. And what is the phase difference between the I and Q RF signals that software-defined radio equipment uses for modulation or demodulation?
Bravo.
Bravo.
Yeah, they're 90 degrees apart. And what is an advantage of using I and Q modulation with software-defined radios?
Wanted ITU zone.
B.
Bravo.
It would be,
Bravo.
yeah, all types of modulation can be created with the appropriate processing. And which of these functions is performed by software in a software-defined radio? Read carefully.
Delta.
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 Filtering, detection, modulation, all of those choices. And what is the frequency above which a low-pass filter's output power is less than half the input power?
Bravo.
Charlie.
Charlie.
It is Charlie. I should have mentioned this specifically. I think it's on the slide. It is the cutoff frequency. And what term specifies a filter's maximum ability to reject signals outside its passband?
Delta.
Delta.
Yeah, that is the ultimate rejection. Yes, indeed. And the bandwidth of a bandpass filter is measured between what two frequencies?
Bravo.
No? That's a good guess, though.
Charlie. Charlie.
Alpha.
It is alpha. It's the half power points, remember, 3 dB. It's the upper and lower half power. They should have put points. That's what they're talking about. And what emission is produced by a reactance modulator, note, reactance modulator, connected to a transmitter RF amplifier stage?
Bravo.
Bravo.
You're not at the oscillator, you're at an amplifier stage, so that's phase modulation. And what is another term for mixing two RF signals?
Alpha.
Yeah, that's Mr. Fesseden's invention. Heterodyning. And what is the stage in an FM or VHF FM transmitter that generates a harmonic of a lower frequency signal to reach a desired operating frequency?
Delta.
Delta.
That's a frequency
Delta.
multiplier. Yeah, we're going to come back to this here in a second. And what combination of a mixer's local oscillator and RF input frequencies is found in the output?
Bravo.
Charlie.
Charlie.
Charlie, it's the sum and the difference plus the original two frequencies. So, all right, we're moving right along. We'll finish this section, then we'll take our 5-minute break. I'm going to push the mute all button. Hopefully everybody's muted there. Good. Let's move on to transmitters. I said the other night I thought the first AM mode, transmitter mode was done with an alternator transmitter. It was actually before that. It was with a spark gap transmitter. It was in 1900. Again, there's our Canadian Reginald Fessenden using a spark gap transmitter. He modulated the amplitude and said, "Hello, 1, 2, 3, 4. Is it snowing where you are?" 1 mile. That was the distance that the radio signal transmitted back in 1900. So again, here's amplitude modulation in the time domain. So amplitude, time, this is what you would see on an oscilloscope, for example, and it's the radio frequency carrier modulated by the modulating signal. That's called the modulation envelope. Doesn't look like a letter, but okay. Modulation envelope. So that's AM. Later on, Edwin Armstrong invented something called a balanced modulator. That was in 1933, so a number of years later. And the beauty of the balanced modulator is that it generates a double sideband suppressed carrier signal. What are you talking about? Remember, AM has a carrier and an upper sideband and a lower sideband. Well, if you process it through a balanced modulator, you get the upper and the lower sidebands, but the carrier goes away. And it looks like this. You have a speech amplifier down here, you have an IRF oscillator here, and by putting it in the balanced modulator, you get upper sideband and lower sideband and no carrier. And on a spectrum display, if you're using a spectrum analyzer, it would look like this. Lower sideband, yes. Upper sideband, yes. Carrier, no. So that's double sideband suppressed carrier done using a balanced modulator. And this brings us to the two methods for generating single sideband in amateur radio equipment. There is the filter method and there is the phasing method. And it's an interesting story because it kind of turns around on us in the end. So back in the 1950s in Iowa, this electronics engineer, brilliant guy, Wes Shum, started a company called Central Electronics. And it pioneered the use of single sideband. And he purported and with his equipment said, the best single sideband we can make is using the phasing method. And he had the mathematics to prove it. And so he went ahead and commercially produced phasing method single sideband generation. And so this is one of the Central Electronics single sideband modulators. And think about, when you get your radio out now, you turn it on and you click a few things and boom, you're there. Think about if you had to do this every time that you got on the air and you wanted to do single sideband. Here's Bob Heil in a YouTube video, a couple minutes, demonstrating how to set this thing up. Oh, and before I do that, though, let me go ahead and turn on original sound so you can hear all the beeps and boops.
And this is how I tuned it up. You'll hear the receiver. We select the band, 80 meters, 75 meters. Then we're going to put this in the carrier null. Now watch. We're going to take those two out of phase, and away went the carrier. There's our carrier null. You can hear in the receiver when I had it up, but very carefully, I'm nulling those two signals, just like with those two microphones. And when we get it all correct, a little I up on top will tell us, but then you can also listen in the receiver. Now we're going to set the max level, and you're going to hear that signal through a receiver when I bring up the microphone.
1, 2, 3, 4. Hello, 1, 2, 3, 4. 1, 2, this is K9EID. K9EID. Hello, 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 hello. 1, 2, 3, 4. 1, 2.
I tuned it off frequency.
1, 2,
so
3, 4.
You knew that you're listening to a sideband signal.
On a Central Electronics 20A and receiving on a CM1 Mosley receiver.
There's the little receiver you're listening to, and I just had it in the background. And there's my scope. And everybody needs a scope. Everybody needs a scope.
600L.
Can you imagine having to do that every time?
600L, no tune linear. It's got a band switch and it's got a meter switch. And these guys today come along with their tens of thousands of dollars in amplifiers. Look at that. Isn't that beautiful? Look at that, George. Is that cool, George?
Bob gets excited. But so that was the phasing method back in the 1950s. It produced a very beautiful signal, but it was too difficult for most hams to use. And the vacuum tubes drifted, requiring retuning, and it produced, as I mentioned, a really clean output, but it lost favor to the much easier to manufacture and use filter method. And the filter method employs that balanced modulator that I told you about. You have your audio coming in to the balanced modulator. Remember, the balanced modulator does not generate a carrier, but it generates an upper sideband and a lower sideband. And you'd be able to build filters that would pass just one or the other. This is the filter method, and then that signal would be mixed in a mixer to go out to whatever frequency that you wanted it to go out to, possibly to be transmitted. So this was much, much easier to use, much, much easier to build, and so the phasing method is dead, right? Well, not so fast, because remember those software-defined radios? What was so difficult to do with tube-type electronics back in the 1950s, remember, all of this stuff can be done in math, in the digital domain. And so an SDR, like the Flex, this is a Flex 6500, is one in which the basic radio functions are performed in software, as we saw, and it's easy to create the mathematical functions of the phasing modulator in software. And because it does generate such a beautiful signal, most SDRs use the phasing method to create single sideband. All right, moving along, something a little bit different. I heard this today. The biggest operating oops. And I'll tell a story on myself here. Dave, if you can come back. Well, let's go to the slide first, because we're talking about split operation. So you got the rare DX station. Here's Mr. DX, all right? And he is transmitting on one frequency. And he says, I'm listening up 5 or up 5 to 20, as I heard today. So he's listening up here. You, as part of the pileup, listen on his frequency and transmit here. This is called split operation. And a great video from Cliff, N4CCB, here is at this link, tells you more about split operation and how you do it on, he's got, I think, three different radios that he shows you how to do it on. Okay, now Dave, you can come back to me. So setting up your radio for split operation is part of being a competent operator, knowing how the radio works. And most every ham gets tripped up on this, whether inadvertently or through confusion or whatever. 2 VFO radios, it's pretty easy to set one VFO on your receive frequency and the other VFO on the transmit frequency, and away you go. The problem is if you lose track of what you're doing, and what you'll do is when the DX station that you're trying to work says, okay, this is Tango X-ray 6 Delta QRZ, and you transmit on the DX frequency, the frequency that he's transmitting on, inadvertently. It happens. I was listening to just that very signal. French Polynesia, TX6D, was operating split this afternoon, and I couldn't tell you how many hams started calling on his frequency. And what happens is you'll get the band police, other hams, who will yell at you then and say, hey, he's operating split, or as the Italians like to say, split. So knowing how to do that properly is really a good skill. Dave, come on back to the presentation here. Remember, in the DX pileups, for the DX station to be able to thin out the herd, he goes split. He transmits on one frequency but listens on another or a range of frequencies. You need to learn how to have your radio be able to be put into the split mode, and the oops comes, and it comes all the time, when you set up wrong and transmit on the DX station's transmit frequency. The embarrassing thing is you transmit your call sign, so everybody in the world knows who it is, including your buddy up in Hendersonville, North Carolina, who was listening on frequency when I did it one time. And he comes on, my friend Bob, and says, "Gary, he's up 5. Was I embarrassed? Here's another pictorial example of split operation. And as I mentioned, radios with dual VFOs can be used for split operation. You put receiver on one and transmit on the other. Dual VFOs are also nice because you can be used to monitor 2 different frequencies. Some radios will allow that. It's called dual watch. So we saw Bob Heil there show off his Central Electronics no-tune tube-type amplifier, which was highly unusual for the age. Most tube-type amplifiers require tuning. So here, by the way, QRP is low power operation. QRO is high power operation. And you need a linear amplifier using the least expensive way to go is high power tubes. And you have a tank circuit right here. It's a pi network circuit. It's kind of like an antenna tuner in a way. And you have your tube here, and you have a plate tuning capacitor, and you have a load capacitor over here. This was the tube type amplifier that I had most recently, a Heathkit SB1000, using 3 500Z tubes. It's got a band switch here that you set manually to the proper band. And then it's got a plate tuning capacitor knob and a load capacitor knob. So it's a pi output like the diagram showed there. And this is the procedure for tuning an amplifier. You set the band switch to the correct band. Don't want to forget that. Then you drive the amplifier with low power, maybe 5-10 watts, and you tune the plate capacitor for a dip in the plate current. You'll see on the meter, one of these it can be set up for the plate current, and one of them can be set up for the grid current. And so you monitor the plate current and you tune it for a dip, the minimum current reading. Then you adjust the loading capacitor for maximum output. Then you go higher in drive, maybe up to 30 watts, retune the plate capacitor for a dip, and then you adjust the load capacitor for maximum output with the plate current not to exceed the tube's ratings, and that'll be in the manual for the amplifier. So this is a tube type amplifier, linear amplifier. You also want to monitor grid current. It's a little complicated, but after a while you can almost do it in your sleep. It becomes almost automatic. One thing you want to make sure with whatever amplifier you have is you don't want to overdrive the amplifier. And tube-type amplifiers have ALC. It's a control signal sent from the amplifier back to the transceiver that reduces the drive power so that you don't overdrive the amplifier. And you need to check the specifications if you get an amplifier to make sure that it's compatible with your radio. Even some of the linear amplifiers push-to-talk circuits, some of them were 110 volt AC, which a lot of modern radios can't handle. So you got to be careful. But for example, here's a Kenwood pair, TS570 transceiver and a TL922 tube-type linear amplifier. In this cable here, it had both the PTT connection and the ALC connection. ALC is the signal sent from the amplifier back to the radio that says reduce your gain. It actually directly controls the radio and says I'm reducing your gain because there's too much coming in to the amplifier. And of course you've got radio energy coming from the transceiver to the input of the amplifier, and the output of the amplifier going out to your antenna. So here's a trick question. Using single sideband, how much power is output when you key your mic but you don't talk? Anybody have an idea?
100%.
Same amount.
0.
Not 100%. 0 is the correct
Really?
answer. Single sideband, if you don't modulate, if you don't talk, there is no output power whatsoever.
I'll be darned.
And so that's the ALC, when it's used with single sideband, actually controls the audio level in the transmitter. So ALC level can be, if you're getting too much ALC back from the amplifier, you can reduce your radio's microphone gain, or the transmit audio level controls. Too much audio gain gives you too much transmitter output and causes ALC to engage. So if you have too much ALC coming back to your transceiver, it doesn't sound intuitive, but you turn down your microphone gain, and that will take care of that problem. Another adjustment that might need to be made in your radio, in the transceiver, driving a linear amplifier, is something called the transmitter delay adjustment. When you push your push to talk button on your microphone, for example, it takes a finite amount of time for tube type amplifiers to flip from receive, it was in the receive mode, to transmit. And that finite amount of time has to be compensated for. And so in your radio, there will be a TX delay adjustment that prevents RF energy output from the transceiver until that set time has elapsed. That allows the relays in an older tube type linear amplifier to make their switch, and it avoids a condition called hot switching. With Morse code signals, the same thing applies, and you can actually see it here on this diagram. With a key down with your Morse code signal, the amp is keyed immediately, but RF from your radio is delayed to give the amp time to flip the relays. Then RF will come out of your radio, and then there's another delay that you can adjust for Morse code called the hang time. It's how long the amplifier stays in the transmit mode. So it doesn't have to go clickety-clackety every time you do a dit or a da. It'll stay in transmit in between the characters. So, but know about the transmit delay. It affects both Morse code and single sideband. More linear amplifier facts, and then we're coming up on a break here. Tube amplifier neutralization. Inside vacuum tubes, there's inter-element capacitance. And because of this, with a tube type amplifier, especially at higher frequencies, the amplifier can oscillate. And actually, it's a runaway situation. It generates a signal when you don't want a signal. And equal to and out of phase signals can be added to cancel out this feedback and putting the tube in a neutral condition. And so that's what is known as tube amplifier neutralization. And here we have a two-tube amplifier. It's a class B, so this is amplifying one half of the waveform. This is amplifying the other. Here's the drive that's coming in. And you notice on the output plate here, there's a tap, and some of this energy is being sent over to this tube, and vice versa over here, the output of the plate, some of it's being sent back over to these are the neutralization capacitors, because these signals are out of phase with each other. And by adding these neutralization capacitors, then it makes the amplifier stable and doesn't generate any parasitic oscillations. Now, if you have a solid state amplifier like myself, the beauty is you don't have to do any tuning. You don't have to do the plate dip. You don't have to do the load for max. But you do have to have band switching going on. And most amplifiers will be able to read the frequency from your radio and do that for you. And solid state amplifiers could be use transistor outputs, either bipolar or MOSFET or new LD MOS devices. But the big thing with solid state linear amplifiers is too much drive power can damage a solid state amplifier. So this is an Elecraft KPA 500. I owned this. It was a very nice amplifier. A friend of mine has it now. And linear amplifiers are Class A amplifiers. They amplify a signal in a linear manner, which means that the output signal looks exactly like the input signal, only higher in amplitude. The output signal is not distorted in any way. And we test amplifier linearity to see how good it is using something called the two-tone test. Hang in there. Two-tone testing uses two non-harmonically related audio sine waves fed into a transceiver's microphone input. So you could have a 1000 hertz sine wave and a 1500 hertz sine wave. They're non-harmonically related. And put those into the input, and what you're looking for at 200 watts, does it look clean? At 400 watts, does it look clean? Yes, okay, we're good. And you use a station monitor scope in order to see that waveform. This is a Kenwood monitor scope. I have one downstairs, and it even has a two-tone generator. You can get the signal out here. Or you can buy two-tone generator kits, or you can get free software to run on your computer. Again, you wouldn't want to have 1000 hertz and 2000 hertz. Those are harmonically related. But 440 and 1000, that's perfect. That would work just great. Two-tone testing for an amplifier's linearity. Overdriving amplifiers is bad whether it's tube type or solid state, and this is what you get if you put too much signal into an amplifier. You get clipping. It's caused by too much signal from the transceiver. And where this can come into play is if you use speech processing. For single sideband and AM modes, you'll find single audio processing built into the radio. It increases the average power level of your signal, which increases the receive intelligibility at the far end. But too much of a good thing is not a good thing. You end up clipping the signal. It should be this, and it's this. The other thing is that when you do that, it creates RF splatter, which makes the signal, which should be clean and about this wide, it gets really wide. And so that 3 kilohertz signal that you thought you had, you might end up with an 8 kilohertz signal because you're splattering so much. And you'll hear people say, hey, you're splattering. And that means you got to turn down a bunch of stuff. Your audio gain, your processing, your compression, your equalization may be wrong, all sorts of different things in order to eliminate that problem. Another thing that, too much of a good thing, background noise. You'll hear room noise, fans going, machinery. If the audio gain is turned up to 11, that's no good. Amplifier efficiency, how much out do you get for how much in? The definition is RF output power divided by the DC input power. It's always going to be less than 1. It's always going to be like 50% or 60%. That's the amplifier's efficiency. We've got so much here. Hang in there, but we're going to get through it. Amplifier classes, these are general amplifier classes. How much of an input waveform does an amplifier amplify? It has to do with how the amplifier is biased. If the amplifier amplifies the whole waveform, it's going to be less power efficient, but it's said to be a linear amplifier if it does that. So here's a Class A linear amplifier. Here's the input signal. It's amplified and it comes out, there's the complete signal. Class A amplifiers are the least power efficient because the DC power is required by the transistor 100% of the time. Class B amplifiers amplify just half of the signal, just going in one direction. And so this is going to be more efficient because the power is only required by the transistor 50% of the time. Now, the problem is that signal there, even if you have 2 of them, is going to sound horrible if it's an audio amplifier because of what they call crossover distortion. So they came up with a mix called a Class AB amplifier, which amplifies all of one and a little bit of the other waveform. It looks like this. This sounds much better as an audio amplifier, and this is what you would find in actual use. Class AB amplifiers are more efficient than A, but less efficient than B, and because DC power is required by the transistor about 60% of the time. The last class is Class C, which could be used for FM or Morse code amplification. It just amplifies a tip of the signal and uses a resonant circuit in the output to make up the rest of the waveform. It's a flywheel effect. And so this is going to be the most power efficient, class C, because in this case the power is required by the transistor like 20% of the time or even less. So on a spectrum here, these are the efficiencies. Class A, least efficient. Class C, most efficient. Is anybody ready for a break? I think I'm ready for a break. Let's go ahead and take our 5-minute break right now, if you don't mind. And then we'll come back, we'll finish out this section, do some questions, and carry on. We are going to probably take the entire night tonight to go up to 8:30, but I will get you out on time, I promise you. So let's go ahead and take our 5-minute break, and we'll be back. Thank you for being patient with us. are back, and appreciate you hanging in there with us. Before we get going, I just wanted to mention, can monitor some of the chat up on YouTube. Somebody asked, can I get my amateur radio license at age 16? Yes. The youngest ham that I know of was about 5 years old. You have to get your technician license first, then the general class, which is what we're talking about here, and then the amateur extra class. But at any age, you can upgrade to amateur extra. And it's just a wonderful hobby with a lot of fun things to do, different aspects that interest you. So yes, get your license at any age. Then another question was, well, how do I get these charts? Well, you can go to the American Radio Relay League's website, arrl.org, and find these charts there, download the PDFs and print them out yourself. Or you can send me an email, w4eey at arrl.net. w4eey at arrl.net, and say, hey, Gary, I would like one of those color charts, and here's my mailing address. And if you do that, I will mail you one of these charts absolutely free. Be happy to do that. All right, let's carry on. We're moving right along. Carson's bandwidth rule. How wide is an FM signal? I don't think this has anything to do with Johnny Carson, but it has to do with the deviation amount and the highest modulating frequency. And so for a voice signal, it would be 3 kilohertz. And for standard deviation in our world in amateur radio, it's 5 kilohertz. So it's 5 plus 3 times 2. So in this case, the bandwidth for our standard signals is 5 plus 3 times 2, or 16 kilohertz. That's Carson's bandwidth rule for FM. All right, remember FM, I talked about those old radios back in the 1950s that used multiplier stages to come up to the operating frequency. Well, they use those stages. Also, the deviation, remember, for FM has to happen at the oscillator stage. And deviation is also multiplied by the same factor. So if you had, well, here's an example. Might be a test question. An operating frequency of 146.52 with a desired deviation of 5 kilohertz. Remember, that's our standard. And we start with a low frequency oscillator of 12.21 megahertz. That's what they used to do. They used to start down there and frequency modulate down there and then multiply it up. And if you take 146, divide it by this 12.21, you'll find it's 12 times. And so to get the right deviation in the end, 5 kilohertz, you take 5 kilohertz and divide it by 12. And you come up with the original oscillator at 12.21 megahertz must be deviated by 416.67 hertz. Frequency multipliers multiply the oscillator frequency up to the operating frequency, and they also multiply the deviation by the same factor. All right, already questions? What control is typically adjusted for proper ALC setting on a single sideband transceiver?
Bravo.
Bravo.
Yeah, it involves the audio section. So transmit audio or microphone gain. If you turn those down, then the ALC will go down. And what is the effect on plate current of the correct setting of a vacuum tube RF power amplifier's tune control? What do you want?
Bravo.
Bravo.
You want a dip in the plate current. And why is automatic level control used with an RF power amplifier?
Charlie.
Charlie is correct, to prevent excessive drive. Good job. And what is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier?
Alpha.
No?
Delta.
It is delta, the desired power output without exceeding the maximum allowable plate current. Most of the time it's just adjusted for maximum output power, and then you'll look and make sure you're not exceeding the max of the tube. So what is the purpose of delaying RF output after activating a transmitter's keying line to an external amplifier?
Charlie. No, Charlie.
It is Charlie. To allow the time for the amplifier to switch the antenna between receive functions and the amplifier's output. And what signals are used to conduct a two-tone test?
Bravo. Bravo.
It is Bravo. Two non-harmonically related audio signals. And what transmitter performance parameter does a two-tone test analyze?
Bravo.
Bravo.
Not Bravo.
Alpha.
Alpha.
Linearity. It's a linearity test, yes. And what is the purpose of a speech processor in a transceiver?
Charlie.
Nope. You want to be heard at the far end.
A.
Alpha.
Alpha, to increase the
Wanted
apparent
ITU
loudness.
zone.
Yeah. And how does a speech processor affect a single sideband phone signal? It doesn't change any peaks, but what it does do is,
Charlie.
Average.
nope,
Really?
Bravo, it increases the average power of your audio signal by using compression and equalization. And what is the effect of an incorrectly adjusted speech processor? Blah, blah, blah.
Wanted ITU zone.
Delta.
Delta,
Delta.
all of those. Distorted speech, excess intermodulation products, excessive background noise, all of those. And what frequency range is occupied by a 3 kilohertz lower sideband signal when the displayed carrier frequency is set to 7.178?
Bravo.
It's lower sideband.
Charlie.
It's going to be Charlie. 7178 is the top end, and you go 3 kilohertz below, so it'll be to 7175. So, yep. And what frequency range is occupied by a 3 kilohertz upper sideband signal with the displayed carrier frequency set to 14.347?
Alpha.
Alpha.
Nope.
B.
Delta.
Alpha.
No, I heard B in there, and you got it. 14.347 up to 14.350. This last digit of the number is kilohertz. So add 3 kilohertz to that, and it becomes 14.350.
50 says Bravo.
So how close to the lower edge of a band's phone segment should your displayed carrier frequency be when using a 3 kilohertz wide lower sideband signal?
A.
Alpha.
Yes, indeed. At least 3 kilohertz above that edge. Correct. And how close to the upper edge should your displayed carrier frequency be when using a 3 kilohertz wide upper sideband?
Charlie.
Bravo.
Bravo, at least 3 kilohertz
Bravo.
below the edge, yeah. And what is the purpose of neutralizing an amplifier?
Bravo.
Yep, to eliminate it oscillating on its own, yep, to eliminate self-oscillations. And which of these classes of amplifiers has the highest efficiency?
Delta.
Delta.
Yep, Class C amplifiers. And in a Class A amplifier, what percentage of time does the amplifying device conduct?
Alpha.
Yep,
Alpha.
100%, correct. And how is the efficiency of an RF power amplifier determined?
Bravo.
See that? Bravo. Divide the RF output, let's say it's 1,000 watts, by the DC input power. It might take 2,000 watts to generate that DC-wise, so that'd be 50% efficiency. That's typical. So which of the following describes a linear amplifier?
The
Amplify frequency.
Be confident, B is correct. An amplifier in
yeah.
which the output preserves the input. Yes. And for which of the following modes is a Class C power stage appropriate?
Delta.
No.
Delta.
No. Because Class C,
No.
remember, is the one that only
Bravo.
amplifies the tip.
Bravo.
Bravo, FM. Yes, correct. And what circuit is used to select one of the sidebands from a balanced modulator?
Alpha.
Nope.
B.
D. Delta.
Bravo.
Nope.
Bravo.
Delta.
There's two methods to generate single sideband, the phasing method and the filter method.
Filter.
You use a filter to select one of the sidebands. And what output is produced by a balanced modulator? This is what you were thinking of.
Alpha.
Nope. A balanced modulator,
Delta.
yes, it generates
Delta.
double sideband suppressed carrier, double sideband modulated RF. There's a lot in this chapter, and you're probably going to have to go back and do some review. So which of the following is an effect of overmodulation?
Charlie.
No?
the excessive.
Delta.
Splatter, yes, excessive bandwidth. Yes, indeed. And what is meant by the term flat topping when referring to an amplitude modulated phone signal?
Charlie.
Charlie, signal distortion, clipping caused by excessive drive or speech levels. And what is the modulation envelope of an AM signal?
Alpha.
Alpha is correct. It's a waveform, and it's a waveform created by connecting the peak values of the modulated signals, the carrier and the modulation. And what is the total bandwidth of an FM phone transmission having 5 kilohertz deviation and 13 kilohertz modulating frequency?
Alpha.
No, this is Carson's bandwidth rule. You may,
16.
Charlie.
yeah, you may have been late coming back from the break. It was 16 kilohertz. It's 5 plus 3 times 2, 16 kilohertz.
Hey, not good.
And what is the frequency deviation for a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation, 146.52 megahertz FM phone transmitter? You might remember.
Charlie.
Nope. Remember, it was a multiplier. We started out at,
Bravo.
Alpha.
it's Bravo, it is Bravo, 416 hertz times 12 would get you up to 5 kilohertz of deviation. All right, this is where we were going to take our intermission, but we had that. So let's move on to receivers. A lot of stuff in this chapter, I know. The simplest superheterodyne receiver is this. It's got a mixer stage. The RF comes in from outside. You've got an oscillator, a local oscillator here, and you get the 4 outputs, the original 2 frequencies, the sum and the difference. And in this case, the difference could be just an audio signal coming through an audio filter and then going out to headphones. And you can actually build simple receivers like this. But more likely, this is what you're going to find on the shelf to buy. A single conversion superheterodyne is one type. The old 5-tube superheterodyne radio, hard to find anymore, was like this, with the radio frequencies coming in, an amplifier stage, a tube maybe, your mixer stage, your intermediate frequency amplifier stage, a demodulator of some type, and an audio amplifier. And remember, we said that we have the mixer stage, we have the original 2 signals, the local oscillator and the RF, the sum and the difference. And another way to look at that is here. Here's our desired station. Okay, this is what we want to receive. And here's our local oscillator signal inside the radio. It's 455 kilohertz higher than the desired station. I'm going to push the mute all button here just ignore if you were requested to unmute. So here's the local oscillator and the desired station. Difference is 455 kilohertz, so the difference will be passed to the amplifier stages and everything's happy. Except that there are two solutions to this problem. If you had an interfering station over here, 455 kilohertz above your local oscillator, the difference of these two signals is also 455 kilohertz. Sorry. Water. And what this means is that you're going to receive two stations instead of one. This is called an image frequency or an image response. Single conversion superheterodyne radios, which have only one mixer, are prone to this. This is a problem, and that's not easily solved in those radios. So what they did for ham radio, which we can't have this, they went to double conversion radios, where you have a first mixer stage, a first IF amplifier, and then a second mixer stage and a second mixer IF amplifier at a different frequency. Doing double and even triple conversions eliminates the image problem, the image frequency that can provide a solution in the single conversion superheterodyne radio. So I want you to think very hoity-toity here and just know that FM is discriminating. I do that because so you remember that a discriminator is the circuit that is used to demodulate FM. You can't use a simple diode detector. You have to use something more complex called a discriminator. Also in our multi-mode radios, this is the ICOM 7300, you're going to probably have attenuator functions. Attenuators are used if you've got a really strong signal or signals coming into the radio. You put the attenuator in and it reduces the signal and it allows the radio to better handle strong signals. The double and triple conversion superheterodyne radios use filters in their IF stages. Filters that are matching the bandwidth of the modulation, 3 kilohertz for single sideband, or maybe 150, 200 hertz for CW. These are either crystal or ceramic filters. They're installed in the IF circuits, and it limits the receiver bandwidth. You want to match the filter width to the mode that you are receiving. Matching that bandwidth to the transmitted bandwidth maximizes your signal-to-noise ratio, gives you the cleanest signal. So that's, you may have actually a knob on your radio that you can select different filters. In digital signal processing or SDR radios, it's continuously variable because it's all done in digital circuits. Notch filters are kind of handy if you've got an interfering carrier that is giving you a whine or a beat in the signal you're trying to receive. You can notch them out. You can adjust it and actually reduce the gain at just that one frequency. They can be in the audio stages or they can be in the IF stages. Audio notch or IF notch. That's a notch filter that's used to remove an interfering carrier. Interference removal is also something that you can use the CW reverse function. ICOM radios have this, others may have it with a different name. You can use either lower side carrier injection or upper side carrier injection to demodulate a Morse code signal. So here's the desired signal. Here's the oscillator, the beat frequency oscillator that's used to give you an audio tone. And here's interference. And it's all within the filter pass band. Well, that's no good. But if you move to CW reverse, then you have your desired signal. You have the BFO below the desired signal. And now the pass band is clean. The interfering signal is outside of the pass band. And you may be able to receive the Morse code signal cleaner. That's CWR, CW reverse. Other knobs that you may have on your radio, IF shift, also known as pass band tuning, allows you to move the IF band pass of your filters up or down in frequency, or widen them out or narrow them up. This can be done in analog and digital circuits. A noise blanker, especially if you're using your radio mobile and you've got spark plug noise or pops and things like that, noise blanker removes regular impulse noise by squelching audio amplification during the noise pulses. So it's not to be confused with a clipper circuit. This is a diode clipper which actually clamps signals to a certain level. This wouldn't be useful. It actually adds distortion. What you want is the noise blanker, which is an active circuit that actually uses the squelch circuit to get rid of the noise. And digital signal processors can be external or internal to the radio. Radio Shack used to sell these outboard digital signal processors. You ran audio into them and they would clean them up. You actually had noise reduction capabilities. You had filters for single sideband and for CW, and bandwidth choices, narrow, medium, and wide. A lot of the radios though have digital signal processing built in to the radio. It's all right there. And digital signal processing does it all. It does noise reduction, notch filtering, noise blanking, audio peak filtering. And with digital signal processing, you don't have to buy the filters. Remember I showed you those filters before? For the big radios, these can be kind of expensive. So with DSP, you can actually save some money. However, too much of a good thing is not so good. If you turn up the noise reduction on digital signal processing too much, you get distortion. Or if you turn down the bandwidth too much, well, you don't get the full signal. So too much of a good thing is not good. Too much processing can lead to distortion. Moving on, in a receiver, you're going to have a signal strength meter. This is showing you the received signal strength. It has S units up to S9, and then it goes in decibels above that, 10 dB above, 20, 30 dB, 40 dB, etc. Each S unit, here's S9, here's S8, is said to be 6 dB. Each S unit represents 6 dB power difference. 6 dBs is 4 times the power. So think about this. If I'm transmitting with a 100 watt transmitter, and my buddy is receiving me at an S5, and I want him to be able to receive me as an S6, I actually have to transmit 400 watts in order to get that signal up to S6. One S unit represents 6 dB. Now, if I have an antenna that can give me directional gain of 6 dB, well, that can do the same thing. So that can raise my effective radiated power in that particular direction. And if you haven't looked at the dB and how it relates to power ratios, here's a table that you can take a look at. I mentioned a beat frequency oscillator earlier. That's used for CW and for single sideband demodulation in a circuit called a product detector, which used a balanced pair of diodes and an injection point for the beat frequency oscillator, receiving single sideband and CW signals. All right, more questions. Let's see how we do. What is the purpose of the notch filter found on many HF transceivers?
Delta.
No.
No.
Charlie.
Not Charlie.
It's one woman, I tell you.
Alpha.
It is Bravo. We went through them all.
It's A, it's B, it's C, and it's not.
Notch filters remove carriers from your receiver passband, which sound like whines or beat frequencies.
If you have a book,
and you can get
the
rid of
answers
it.
are right there.
You can do it. Now hang in there. So what is the benefit of using the opposite or reverse sideband when receiving CW?
Charlie.
Exactly.
Bravo.
It may be no, it's Charlie. It may be possible to reduce or eliminate
Like that one there,
interference
the guy said
from
Charlie,
other
and
things.
she said Bravo.
Okay, that's okay. Let's be nice.
Charlie.
Let's be nice. Let's be nice. how does a noise blanker work, okay?
C.
It is C, by reducing receiver gain, squelching out noise peaks or pulses, so yes. And what happens as a receiver's noise reduction control level is increased? Too much of a good thing? Alpha, the received signals may become distorted. And what is the purpose of using a receive attenuator?
A.
Yes, indeed, to prevent receiver overload from strong incoming signals. And what does an S meter measure?
C.
Yep, received signal strength.
Charlie.
Yep. And how does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated meter? So 10 dB, if you remember, is 10 times, and 10 plus 10 would be 20. So 10 times 10, I'm going to give you this one to you, it's 100 times more powerful. Something that is 20 dB more is 100 times more powerful. And how much change in signal strength is typically represented by 1 S unit?
Alpha.
Yep, 6 dB, or 4 times. And how much must the power output of a transmitter be raised to change the S meter reading from S8 to S9?
Charlie.
Yep, 4 times. And how is a product detector used?
Delta.
Delta.
Delta, perfect. Used in a single sideband receiver to extract the modulated signal. It's also used for Morse code as well. And which of the following is an advantage of a digital signal processing filter compared to an analog filter?
Bravo.
No, actually you need more
Alpha.
digital components. It's alpha. A wide range of filter bandwidths and shapes can be created. And which parameter affects receiver sensitivity? Read carefully.
Delta.
Yeah.
I'd say
Delta.
Yep, the input gain, the demodulator stage bandwidth, the input amplifier noise figure, all of those factors can affect a receiver's sensitivity. And which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency?
Bravo.
The local
Frequency,
oscillator
delta.
is correct. No, Bravo is correct. For the first mixer, you got the RF coming in, and you got the local oscillator, and the output is the IF frequency. And what is the term for interference from a signal at twice the IF frequency of the desired signal?
Would be Charlie.
No. This is the problem with super heterodyne radios of only a single stage.
Alpha.
Bravo.
It is Bravo. It's the image.
Bravo.
We're talking about image problems. Yeah.
She just goes till she gets the right one.
Well, I do the same thing. So why is it good to match receiver bandwidth to the bandwidth of the operating mode?
I'm gonna go potty.
Okay.
Delta.
It is delta, and it results in the best signal to noise ratio. Okay, guys, it's a long night tonight. I pushed the mute all button. Let's do the last section, probably the funnest one, high frequency station installation. How'd you like to have this station? This was my friend Bob's about 4 years ago. It's probably changed considerably. ND7J up in Hendersonville. So he put his station together using transceivers. What do you got there? Oh, this is old TS2000. I know that's gone. Yeah, it's different now, but that was Bob's. This was my old station at my old QTH. My flex radio then was back there, and I was controlling it using the monitors. A little closer view, there's the Flex 6600, my German RF kit solid state amplifier, a Maestro controller. Okay, that was then. This is now. This is my station today. With the radios off in another room, the controller here, the monitors. Then I have a VHF and UHF operating position. The whole point of all this is how you put your station together is up to you. What is it that you want to do? Do you want to be net control for a local net? Or do you want to work DX or contest or whatever? That's going to determine how your station gets put together. However you decide, you're going to want to use some good principles, some good engineering practices in putting your system together. One of those is to try to eliminate radio frequency interference to your station. You can use grounding and bonding techniques, keeping the ground connections on the back of the radios connected together. You can use shielded cable even for DC power. We'll talk about ferrites here in a little bit. They can give you solutions to problem cables. You want to try to, if you can, keep your antennas away from your ham shack. I put my antennas in my first ham shack right above the ham shack on a roof tower, and I had no end of problems. Now my antennas are well away from the ham shack, and it's much, much nicer. And if you can, use balanced antennas like dipoles or even verticals that don't work against station ground. So here's intermodulation. This is the top of a look kind of like Paris Mountain over in Greenville, South Carolina. Lots of towers, lots of transmissions from pagers, cell companies, broadcasters, studio transmitter links, all sorts of stuff up there. And those signals can interfere with each other. So I'm going to tell you a brief story. We're going to move through this quickly because I want to get you out on time, I promised. So back in the day when I worked for Voice of America, I was assigned to my first overseas assignment to Liberia, West Africa. If you take a look here at the map, you can see that we were stationed at Carisburg, which is right there. The capital of Liberia is Monrovia, right there. We were out in the middle of nowhere out there on a 2,000-acre compound with high-power broadcast transmitters. And actually, ham radio was a godsend because it allowed me to communicate regularly back into the United States. And my main radio at the time was this, Kenwood TS-180, ham band only transceiver, all solid state. And that was great. And connected it up to my 4-element TET beam and was able to get back to the States no problem whatsoever. So Liberia also was home to a lot of other facilities. One of them was Elwa, which was a missionary radio station closer in toward Monrovia. And there was a lot of other missionary activities going on in Liberia when I was there back in 1990, 1991. There was a missionary radio net, actually, on 80 meters. And it was, for them, their reliable means of communication. And I wanted to participate, so I put up an 80-meter dipole, and I decided to add, I had a second radio with me, so I'm going to put a second radio in my station. And so I added this Kenwood TS-440 to the 80-meter dipole, and I had no end of problems after I plugged that antenna into the back of the radio, because then my original radio, the TS-180, on 20 meters to the States, was wiped out completely. I couldn't hear anything. I thought, what the heck is going on? Well, here, this is the antenna farm at the old relay station. You know, we had 2,000 acres of these curtain antennas with 20 dB of forward gain, and we had lots of radio frequency signals, and inside the new radio, the 440 that I'd put, were bandpass filters like this and diodes. See the diode there and the diode there? These were used to select which filter, and when I plugged that antenna in the back of the 440, maximum intermodulation distortion occurred. Because VOA was transmitting on various shortwave frequencies, and they all mixed together, causing noise on the first station. The solution, I had to remove the antenna cable from the second radio at any time I wanted to use the first radio on my beam antenna. I QRM'd myself. So that's intermodulation distortion, which is interference caused by mixing or heterodyning two or more other signals in a non-linear device. And we're going to look at a formula here in a second. F1 is the frequency you're trying to receive, and F2 is an interfering frequency in the formula. And so here we have, here's F1, that's the frequency you're trying to receive, and here's F2, the interfering, and you'll find that there are all sorts of mixing products that are generated. There's one over here, F2 minus F1, there's some over here, 2 I can't even read it. I don't have my glasses on. There we go. 2F1 minus F2. So these are the first order products. These are the fundamental frequencies. Second order products are when there's an even number, 1F2, 1F1, and third order products are when it's 2 and 1. Let me show you here. This is a third order product. 2, and there's a 1 that's implied over here. 2 and 1 is 3. These are the pesky interference products that would be close in to the desired frequency. So what you need to know is odd order products, third order products are always the problems. Third order products are these interfering signals that are close in to the original two frequencies. They're going to cause you the most problems. And third order products are odd products. Just know that. We don't have time to delve deeper into this. I apologize. So RF in the shack, if you have your antennas too close to your ham shack like I did for so long, can cause distortion in your mic audio. It can cause your transmitter to lock up, and can cause disconnects to USB, Ethernet, and other control signals. And how do you fight this? Well, you can use grounding and bonding, making sure that all of the chassis of the equipment are connected together. Ferrites can fight signals on cables, and bypass capacitors in audio circuits. Now, the worst case is when you transmit and you touch a piece of equipment and you get an RF burn. That can happen, and so again, the solution is to bond all equipment together. I'm going to send you this link, and I'll mention it also in an email. This is an excellent video to watch called Standing Up for Standing Waves, done by Gary Pierce at Ham Radio Now. And two things I want to pull from this presentation, that two rules. That a quarter wavelength long wire is what they call an impedance inverter. And a half wavelength piece of wire is an impedance repeater. You can watch the video and get more details on that. It has to do with how long your ground connection cable is. When your ground wire going to a ground stake, pounded 8 feet into the ground, if it's a quarter wavelength long, it might as well not be there. Or if it's quarter wavelength or a multiple of a quarter of a wavelength, it looks open. It looks like there's no connection whatsoever, because a quarter wavelength wire is an impedance inverter. It's ground at one end, but wide open at the other end. And that's known as a resonant ground connection. It's said to have a high impedance at a particular frequency, and this can allow high RF voltages to exist on radio frequency chassis. Now, the ground rod itself that you pounded 8 feet into the ground is still good. It's not resonant itself. A ground rod is a ground rod. But the ground connection, the wire, the quarter wavelength long, can be an open circuit at that particular frequency and not be good. So the ground connection can be said to be resonant, not the ground rod. When you're doing grounding and bonding, when you're bonding equipment together, it's always best to go to a single point ground. rather than have a bus bar, a long bus bar, and connecting equipment to it. At audio and DC, that's fine, the bus bar, but at RF, you get all sorts of RF ground loops. And when this happens, you can get hum in your audio, or you can get distortion and lockups with RF. So use single point grounding, that works better. In your car, radio power connections always should go back to the battery, and separate parts of a vehicle's body may need to be bonded together with conductive braid. And in autos, you can find all sorts of interference sources, fuel pumps, onboard computers, even the electrical systems, battery chargers inside can cause you noise on your HF radio. 12-volt outlets for radio power, probably don't want to do that because the outlet's only probably rated at 10 amps, and your 100 amp HF transceiver is going to draw a lot more power than that. So you want to go all the way back to the battery with your power connections. If you're getting distortion and somebody says, hey, your audio is sounding kind of fuzzy, it may be RF getting into your microphone. And one way you can eliminate that is by adding small capacitors, 0.01 microfarad, for example, inside the microphone capsule. That will short out the RF while allowing the audio to pass. Those are RF bypass capacitors. Arcing, if you have an arc nearby, you're going to get wide bands of noise, and you're going to hear it on your radio. So just remember that arcs cause noise. Can a telephone receive single sideband? Not very well. You get distorted speech. You can't understand what they're saying. Can a stereo receive Morse code? Very poorly. You get humming and clicking. And we're going to talk more about this later, but on the outside of the shield of a coaxial cable, it's completely independent of the inside of the shield and the center conductor. There are actually 3 conductors in a coax, and the outside of the coaxial cable can contain common mode currents. And to block those, you can install a ferrite. This is a ferrite toroid with a cable wrapped through it to get additional impedance. Ferrites impede RF current on the outside of coaxial cable, and sometimes this can eliminate interference. And for cars, the antenna is always the problem. The low efficiency antennas on cars limit the amount of signal that you can get out, and probably don't pass the wife acceptance factor. All right, last set of questions, and then we can be done. Which of the following might be useful in reducing RF interference in audio frequency circuits?
Bravo.
Yep, the RF bypass capacitor. Yes, indeed. And which of the following could be a cause of interference covering a wide range of frequencies?
Charlie.
Yep, arcing. And what sound is heard from an audio device experiencing RF interference from a single sideband phone transmitter? Like a telephone?
Charlie.
Yep, distorted speech.
Distorted speech.
And what sound is heard from an audio device experience interference from a Morse code transmitter?
Alpha.
Yep,
Alpha.
Humming and clicking. And what is a possible cause of high voltages that produce RF burns?
Delta.
Yes, the ground wire might be a quarter of a wavelength long, so it has a high impedance on that frequency. And what is a possible effect of a resonant ground connection? It's another way to ask the same question. Yeah, Charlie, high RF voltages that'll bite you. And which of the following could or would reduce RF interference caused by common mode current on an audio cable?
Alpha.
Yep, ferrites. Ferrites are your friend. Place a ferrite choke on the cable. And how can the effects of ground loops be minimized?
Alpha.
No, it's Delta.
Delta.
Bond equipment enclosures together. Don't rely on the audio or RF cables connecting them together. Bond the chassis together. And what could be a symptom caused by a ground loop in your station's audio? Hum. Yeah, you receive reports of hum on your station's transmitted signal. And what technique helps minimize RF hotspots? Another way to ask the question. Charlie, bonding that equipment together again. Yep. And why must all metal enclosures of station equipment be grounded?
Bravo.
No, not Bravo. It ensures that hazardous voltages can't appear on the chassis. There's different ways of asking the same question. So which of the following direct fused power connections would be best for a 100-watt HF mobile installation?
Alpha.
Yep, to the battery using heavy gauge wire. Yeah. You don't want to use transmission line. You want to use heavy gauge wire. Why should DC power for a 100-watt HF transceiver not be supplied by the cigarette lighter socket?
Bravo.
Yep, the socket's wiring may be inadequate for the current drawn. Yeah. And which of the following most limits HF mobile installation? Other than the wife, who won't let you put it in. It's the electrically short antenna. Those antennas are always the problem. And which of the following may cause receive interference to an HF transceiver installed in a vehicle? Read carefully.
Delta.
Yep, every one of those. Battery charging, fuel delivery, control computers. And how does a ferrite bead or core reduce common mode RF current on the shield of a coax?
Charlie.
Alpha, by creating an impedance in the current's path. And which intermodulation products are closest to the original signal frequencies?
Alpha.
No, odd order or
Charlie.
third order. Yep, Charlie.
Charlie.
It's a big topic and we didn't have a lot of time. What process combines two signals in a nonlinear circuit to produce unwanted spurious outputs? The thing I experienced in Liberia? Intermodulation.
Alpha.
Yeah, intermodulation. And which of the following is an odd order intermodulation product?
Delta.
Bravo.
It is Charlie, because there's two and there's a one, and they had to get it's three, so that's odd. I apologize, but that is the end of chapter 5. We made it. It was a yeoman task. Come on back to me if you would, Dave, please. Thank you. Great job. I'll do better next time. I promise you.
No, you.
Thank you, Gary.
Your head is going to explode, I
You
know.
did good this time.
Dave,
Thanks a lot.
tell us about chapter 6 next week. Anything?
Yep, in about 10 seconds. We're going to cover all of chapter 6 next week. And I'll be sending an email out so you can get started by reading through that chapter. Now, digital modes are probably one of the fastest growing things in amateur radio. And I think this will be a very valuable chapter. If we have time at the end, I'll actually do a supplemental section on FT8. So that's for next week. Watch for an email.
All right, 73, y'all. Have a great night.
73.
Thank you.
Thank you.